Good afternoon. We'll start our class.
Good afternoon, ma'am.
Good afternoon. So we will start our new chapter, that is the entropy chapter. So far we have discussed the second law, second law statement. Then we have also seen the application of second law in the cycle. So that is heat engine cycle, Carnot heat engine cycle. So till now we have discussed application up to the cycle. So like in case of the first law, there we were using that first law to the cycle, as well as we are using for the process. So similarly, in case of the second law also, that can be applicable to the process. So when it is applicable to the process, um, it will give the new property. That property name is your entropy. Okay. So like in case of the first law, when it is applied to the process, it will leads to the definition of the internal energy. Like that, in case of the second law, when it is applicable to the process, then it will lead to the definition of the entropy. So in case of the thermodynamics, we will come to know about the 3E. 3E is about your energy, equilibrium, then entropy. Whenever we are discussing any means any uh, problem related to the thermodynamics, always we are discussing these three terms, that is your energy, equilibrium, and entropy. Okay, so that entropy is a property of the system that we are going to discuss here. Then we will discuss the entropy principle, what is that one, and about the application of the entropy principle. So first, I will discuss some theorem or any statement that is related to the entropy. First, that one I will discuss. Then I will go to the proof of the entropy as the property of the system, that I will discuss. So first statement I am going to prove is your, that is your two reversible. Okay. So this statement is two reversible adiabatic paths cannot intersect each other. So from this statement, we can know that here it will lead to some property definition. So that one we'll discuss here. So to prove this one, to prove this statement, we have to assume that the two reversible adiabatic paths intersecting intersecting each other. Okay. So if you are taking this assumption and we are drawing in a PV plot, then it will look like this. It is your PV plot. So let us consider that there is the two reversible adiabatic path. Let us this one is the A. Okay. Another one is the path is your B, which is intersecting A at the point C. So this one is your reversible adiabatic path. So little bit it will be stepper one. Let me draw it properly. So like this it will be, it is the B and it is your C, sorry A. So A and B both are reversible adiabatic path which are intersecting at the point C. So let us consider that another line we are drawing from path A to path B. That line is nothing but that is the reversible isotherm. So this is a reversible isotherm. So let us take the arrow mark if we are giving like this. That means it is the process is going on like this. So this line is a reversible isotherm. So all of you know that heat addition and rejection is possible in case of the reversible isotherm process. Okay, so in case of the reversible adiabatic path, there we are having the expansion and compression work. Okay, so keep the arrow mark. So it will look like this. So initially we are assumed that this path A and B both are reversible adiabatic path, both are intersecting at the point C. Then we are drawing another isotherm line which will cut both the path A and B, and through which there will be the heat addition or um, heat absorption will take place at the constant temperature. So if you will see, this will form a thermodynamic cycle. It is complete cycle in which the uh, process will be like this: one, two, C1. Okay, so in this case, if it is a thermodynamic cycle, here some work transfer will be there due to the heat addition. So we can say that in this thermodynamic cycle, there is the net work output. So let us consider that is the W net, net work output in the thermodynamic cycle by the heat addition in the reversible isotherm. So by looking at this diagram, we can uh, 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 what I can say. We can conclude that in this case, there is the continuous work output in the thermodynamic cycle by transferring heat with the single phase temperature. So there is only one temperature, constant temperature at which heat is added. But if you are observing here, there is no heat rejection. Okay, so this statement will violate the Kelvin Planck statement. So it will violate the Kelvin Planck statement. Please wait for a minute. भाई तुम लोग जाओ यहाँ से. Sorry for the disturbance. Okay, we'll continue our class. So this diagram will violate the Kelvin Planck statement. So that statement is which we have assumed that is not correct. So what is then it is correct? It is correct is two reversible adiabatic paths both will not intersect each other. So both will be the separate one. Okay. So there at one point there will pass at one point means it is reversible isotherm. So at the one point of the reversible isotherm, there can pass only one reversible adiabatic. Okay, so something it will be look like this as per this statement. Okay, so it is the reversible isotherm. This one is the reversible adiabatic. Another one is the reversible adiabatic. So now it is proved that two reversible adiabatic paths will never intersect each other. Okay, so this statement will be utilized to find the entropy relation. So in that part. So again, we will discuss the Clausius theorem. What is that one? Okay. So what is that theorem? For that one, we have to draw the PV plot and we have to consider the one process. So through which at one point there will be the passing of the reversible adiabatic, and another point there will be also passing of the reversible adiabatic. Okay, use this diagram. So let us consider what is Clausius theorem. To that is the Clausius theorem means in this case we have to find that the cyclic integral of your dq upon t in the reversible cycle is equal to your 0. So this is known as your Clausius theorem. So in which we have to find that cyclic integral of del q upon t for a reversible cycle will be equal to 0. Okay, so how it is possible that we are going to see. So let us consider that there is one process in which that system will be taken from the point I to the point F. So let us take this uh, idea that that system will be taken from the state one equilibrium state, that is I, to the another equilibrium state F, by following the reversible path. So this path is your reversible path. So IF is nothing but it is one path, that is the reversible path. Okay, so let us take that one line which is passing through the point I. So draw the line like this. So let us assume that this line is nothing but it is the reversible adiabatic line. So let us give that name, that is your A. This line name is A. Then another line we will draw from the point F, equilibrium state F. So let us take that line is also a reversible line. Okay, so it is also a reversible path, or this path is known as your reversible adiabatic path. Let us consider this is the path is or line is your BF. Okay, so this is the reversible adiabatic path which is drawn from the point F. Okay, so now let us draw another line from A to B, which is known as the reversible isotherm. Okay, so AB is nothing but it is the reversible isotherm line. And this line is drawn in such a way that the area under IABF is equal to the area under the IF. So this line is drawn in such a way that area under IABF is equal to the area under the IF. Okay, so please write down that one. I'll write that. I'll write that one. Um, line AB is drawn in such a way that area under IABF is equal to your area under IF. अब ये बताइए एरिया अंडर IABF मीन्स ये क्या होगा? पीवी प्लॉट में अगर कोई भी प्रोसेस के अंडर में हम एरिया ले रहे हैं तो वो क्या रिप्रेजेंट करेगा? कौन सा चीज वो रिप्रेजेंट करेगा? एनीवन ऑफ यू?
Work.
वर्क. Okay, Kumar Bhairav, right? What is the roll number?
44.
44. Okay, so your it will represent area under the curve is nothing but in the PV plot is nothing but it is the word transfer. Okay, so if we are representing area under the IABF means we can write like this. It is the word transfer, that is IABF. Okay, which is equal to the area under IF. So in this process, the work done will be, we can represent work transfer will be the WIF, right? So we have taken this assumption. So as per that one, the work transfer will be same. Okay, so if you are observing this diagram, this diagram will is related to the previous statement. So here we have concluded that two reversible adiabatic paths will cannot intersect each other. Okay, so this reversible adiabatic path can pass at one point. What my point? Another thing is that reversible adiabatic means that these two will be the um, constant property line. Okay, so when we are discussing two constant property line, then in that case these two constant property line will never intersect each other. That is also one thing. Okay, so we will see that one later on. So from this diagram, we have taken this assumption. As per this, we are getting the word transfer is same. Okay, so now we have to consider the process that is your process IF. So in case of the process IF, if it is applicable to the, if you are using the first law, in that case, we can write on our equation that is your Q equal to your delta U or delta E plus W, right? So in this case, Q will be the QIF heat transfer in the process IF, and W will be the work transfer in the process IF. So similarly here in this case it will internal energy change will depend upon the end state. Okay, so end and means it will depend upon the, it is the difference of the final state and initial state. So if you are writing this equation, it will be the QIF, which is equal to your UF minus UI plus WIF. So similarly, process IABF, if you are writing the for the process IABF, then we can write down as QIABF is equal to, in this case also it internal energy change will be the difference of your UF minus UI plus there is work transfer in the process, that is your WIABF. Okay, so this relation we will get. So if you are observing in these two equation, so let us take it is the one and this one is the two. If you are observing these two equations, then UF minus UI is both is common in this case, and another is your word transfer. In this case, both word transfer is same. If both the word transfer is same, then it will cancel out, and this will also neglected. And then what will be the remaining thing? In this case, your heat transfer will be the same. So we can write that QIF is equal to your QIABF, right? So we can write like this. Then this QIABF will be become the heat transfer in case of the IA as well as AB. Then it is heat addition in this BF process. So all the three process, whatever heat transfer will be there, that will be added, and we will get the total heat transfer in the QIABF process. So I can write like this: it is the heat transfer in a EA, IA, then it is the heat transfer at AB, then it is the heat transfer at BF. So if you are observing in this case, it is the reversible adiabatic path, and BF is also reversible adiabatic path. So if it is a adiabatic path, then Q will be the 0. So then we will have only this term, that is QAB. So there is only heat transfer in the reversible isothermal process. So that we can conclude as QIF is equal to your QAB. Okay. So from this statement, so from this relation, we can say that the heat transfer in the process IF is equal to the heat transfer in the reversible isothermal process. That is your AB. Okay, so we can say that this reversible path will be substituted by the reversible zigzag path. So what is zigzag path? This is one path, another is the reversible isotherm, then it is the reversible adiabatic. So it will be substituted by the reversible zigzag path. Okay, so we can conclude it from this relation as any reversible path. Okay, not my point. So there is heat transfer is possible in case of the isothermal process. So as we have written that Clausius theorem is applicable to the cyclic process. Okay. So for that one we have to take one cycle, and we will discuss the individual process. जो ये हमने डिस्कस किया है यहाँ पे, ये स्टेटमेंट लाने के लिए इसको यूज करके हम ये जो रिलेशन है उसको फाइंड आउट करेंगे. ओके. So to prove our Clausius theorem, and in that case we have to take one reversible cycle, closed cycle. So let us take one reversible cycle. So let us, this is the reversible cycle we have taken. So in this case, if we are drawing one line at one point, so this will be become the reversible adiabatic. Okay. So suppose uh, this cycle is divided into the number of the elemental cycle, means small cycle. So how this cycle can be divided into the elemental cycle, I will also you here. It is your PV plot. Here we have taken one reversible cycle. So initially we will got the one line, we will draw one line, that is the let us consider that is a reversible adiabatic. Then we know that one reversible path will be followed by the substituted by the reversible zigzag path. So let us take it is one line, then we will draw the zigzag one reversible isotherm which will cut the reversible adiabatic. Similarly, we will draw another line from this point. So this will be another reversible adiabatic. So likewise, if we will draw the line like this, now we can see that it is divided into the number of elemental cycle. So like that, we have to draw the zigzag path. So similarly, okay. Okay, so something it will look like this. So let us take these two elemental cycles. So in which, so there is the reversible two or reversible isotherm. So in which there is the temperature is T1. In this case, this will be the temperature is T2. So if it is divided into the elemental part, then your heat transfer will be the dq1 and it will be the dqt. एलिमेंटल पार्ट में डिवाइड किए हैं इसलिए यहाँ पे हीट ट्रांसफर हमने dq1 dq2 लिए हुए हैं हीट एडिशन एंड हीट रिजेक्शन के लिए. Similarly in this case it will be the dq2, here it will be the dq3. Okay, so let us give the name that is abcd like that. A B C D, here it will be the E F G H. Like that we can give the name to other elemental cycle. Okay, so now we will consider the one element cycle that is your ABCD cycle. In this case, there is the heat addition is dq1 at the constant temperature T1. Heat rejection is your dq2 at the constant temperature T2. Okay, so if we will write this equation in like the absolute thermodynamic temperature scale, then equation we can write as dq1 upon dq2. It will become the T1 upon T2, right? So we can write like this dq1 upon T1 is equal to your dq2 upon T2. Similarly, for the cycle, elemental cycle that is your EFGH cycle, we can also write down this heat addition and heat rejection equation that will be the dq3. So this one will be the dq3 and dq4. This is your dq3. This one is the dq4, right? dq3 upon t3 is equal to your dq4 upon t4. Okay, so for these two cycle I have written like this. So similarly for the other elemental cycle, we will get the relation like this. Heat transfer and temperature relation will be like this. Then if you are bringing this equation to the left side, it will be the dq1 upon t1 minus dq2 upon t2 is equal to your 0. So if you will put the sign convention as the negative one, heat rejection is the negative, right? So if it is the negative, then it will become the plus. Then we will get the relation dq1 upon t1 plus dq2 upon t2 is equal to your 0. Similarly, in this case also, if you are taking the heat rejection as the negative, then it will become dq3 upon t3 plus dq4 upon t4 is equal to 0. Okay. So for the number of elemental cycle, we can write this whole equation. So for the whole cycle, we can, for total cycle, as I have told you, it is a reversible cycle. Reversible cycle means it will, we can say it as it is the Carnot cycle, right? In which all the processes are reversible one. Okay, for the total cycle, we can write the equation is dq1 upon t1 plus dq2 upon t2 plus dq3 upon t3 plus dq4 upon t4 is equal to 0. So it will be become the cyclic integral of dq upon t is equal to 0 in a reversible cycle. So now we have found that as per the Clausius theorem, cyclic integral of t in a reversible cycle is equal to your 0. So we have proved this relation. So from this one, we can find out that this relation will lead to the property that is the entropy of the system. Okay, so now suppose we are going to prove that property of entropy, that entropy is the property of the system. Like in case of the first law, we have also derived this one, the property of system. Okay, so in this case, we will draw the reversible path. Two reversible path we will draw in the PV plot. Okay, so let us take that one system is taken from the equilibrium state to the another equilibrium state, that is the F, by following the reversible path R1. Then it is that system is again bringing back to the state I by following the reversible path, that is the R2. Okay, so if you are observing this diagram, then it will be become a cycle, so which is the reversible cycle. So for that one, if you are writing the equation, Clausius theorem, in which del q upon t will be 0. Okay, so this is the in case of the reversible cycle. So where we are having the two reversible path, that is R1 and R2. Okay, so in this case, this cyclic integral, it can be written as, it is for the individual process we can write as R1 reversible path dq upon t plus f into I by reversible path to dq upon t is equal to 0. Okay, so we can break this into reversible path, which is equal to your addition is equal to your 0. Then we can also write like this, if dq upon t. If we will bring this relation to the right side, then it will become r2 f I dq upon t. So it will become minus. Okay, so because we are bringing to the right hand side, so it will become minus. We know that it is R2 is nothing but it is the reversible path. Reversible path means again we can bringing back to I to F by following the path R2. So reversible path means we can reverse the direction. Okay, so if you are reversing the direction in this case, this will become the plus. So I can write down. That one seems R2 is reversible path. Then we can write like this IF R2 dq upon t is sorry fi minus it is the IFR dq upon t2. So then this side will be the right hand side will be become IF R2 dq upon t. Okay. IF R1 dq upon t is equal to your IF R2 dq upon t. So if you are observing these two reversible equation in this case, both end state are same. So whatever it is the path following, but the end state are same. So the end state are I and F. So as for this relation, we can conclude that there exists one property of the system. That property is known as your entropy. Okay. So whatever the mm, 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 whatever the path is followed, that will dqt will not depend upon that one. It will depend upon the end state. Okay. So here we will find that it will, if it is depend upon the end state, then that will be the property of the system. Okay. So we can say that the relation I f in the reversible path dq upon t will give will lead to the generation of the property. It will lead to the definition of the property. That property is nothing but that is your entropy. Okay, so which will depend upon the final state of the system. So initial and final state of the system. So we can write as it will be the difference of the SF minus SI. Then this term will give IF will give you as dq upon t is nothing but it is the SF minus SI. Okay, so suppose these states are I and F are both are infinitesimally near. In that case, we can write like this: del Q in the reversible path upon T is equal to your ds. Okay, so it is the entropy of the system. Okay, so this entropy, is this relation is only applicable for the reversible path dq upon t. ओके, इरिवर्सिबल पाथ के लिए आपका एंट्रोपी चेंज अलग हो जाएगा, जो कि हम ओपन सिस्टम एंड क्लोज सिस्टम में एप्लीकेबल के लिए अलग अलग डिस्कस करेंगे. तो आपके लिए जो इरिवर्सिबल प्रोसेस में एंट्रोपी कितना जनरेट हो रही है वो आपके सिलेबस में नहीं है, तो उसको मैं डिस्कस नहीं करूंगी. Only I will discuss up to the application of the entropy principle. Okay, so your temperature entropy plot will give you the, suppose you are having the temperature and entropy plot, and there is one process is going from the I to F. That means any system which is going from the I to F. In that case, the area under this curve will give you the area under this curve will give you the heat transfer. Okay, got my point? So heat transfer can be represented as Q reversible integration of your TdS I to S. Got my point? तो पीवी प्लॉट में जो एरिया अंडर द कर्व हमको वर्क ट्रांसफर मिल रही थी, टीएस प्लॉट में एरिया अंडर द कर्व विल गिव यू द heat transfer. Okay, so this relation is for the reversible path. So this I can write like this: T E Q is equal to your T into SF minus SI. Got my point? So what is entropy? Entropy is, we can say it is the temperature dependent property. So if there is the heat transfer at the constant temperature, then we will have the entropy transfer or entropy change. Okay. So there is the increase of the temperature. So as per the entropy principle, when we are discussing in the next slide. So as per the entropy principle, the entropy will always increase in condition. It will never decrease. Okay. So it will become constant when the or reversible process will achieve, or reversible path will achieve. It will never decrease. Okay. What my point? So entropy is nothing but it is the measure of the. Okay, so it is nothing but it is the molecular disorder, or it is the molecular randomness. So what is molecular disorder? So whatever the changes will occur at the molecular region, so that we can say that molecular disorder. So suppose we are taking the example of your solid and your gas. Okay, so solid meat in this case, the molecule are closely packed in this case. So at fixed position, at particular position they will vibrate. Okay, at fixed position or equilibrium position they will vibrate. But here in this case, those will not move here and there. Random motion is absent in case of the solid, but in case of the gas, there is the molecule can move here and there. Their motion is not predictable. Okay, so that for in that case, they will not oscillate at like your solid case. In this case, the molecule will oscillate about their equilibrium position. But in this case, they will move randomly, and they can collide with each other, right? So if they are colliding with each other, then there will be the extreme change will be possible in this case. So in this case, due to that molecular randomness, your entropy or disorderness will increase. Okay, got my point? So that entropy will depend upon the temperature. When your temperature is increasing, in that case, molecular disorder will increase or randomness will increase. Okay. So when your temperature is decreasing, temperature is dropping, in that case, what will happen? The molecules will become supposed to be motionless at the absolute zero temperature. But that order, the means the state is what I can say in that case, that state is we cannot say that it will become zero. In that case, the entropy will become zero. That will anyhow it will exist. It will exhibit a minimum energy. Okay, though we are decreasing the temperature, their state will have the minimum energy. Okay, due to this molecular, as per the molecular order. Okay, so we can say that at absolute zero temperature, that molecule will become motionless. Okay, so here we can uh, uh, we can know about the third law of your thermodynamics. What is that one? Third law of thermodynamics. The third law of thermodynamics means in which we can say that that statement is at the absolute. Mm, in that case, the entropy of of a pure crystalline substance at absolute zero temperature is zero. Okay, so this is the third law of thermodynamics, in which we can say that entropy of pure crystalline substance at absolute zero temperature is zero. Okay, so for the pure crystalline substance only this is possible. Okay, so that is related to the solid phase of the substance. So in that case, we can say that your as per the temperature decrease, that motion of the molecule will become zero at the absolute zero temperature. Okay. So many practical example you can consider to discuss this entropy, as it is the disorder, molecular disorder or randomness. Okay, so when you are following the normal life, or means disciplined life, means more punctual life, in that case your entropy is low. If suppose you are not following any disciplined life, in that case your entropy will become high, because suddenly you will get angry, suddenly you will react. In that case, we can say that that is the nothing but it is the increase of the entropy. So like that, we can take some practical examples also. Okay, so there is one term, that is your Clausius inequality. Okay, so I'm not going to derive this one. So only I will tell you the final term. What is Clausius inequality? So Clausius inequality means it is the cyclic integral of your del q upon t is less than equal to zero. Okay. So how this term is achieved? It is derived from the relation, that is the dq upon t less than equal to your cyclic integral of your ds. Okay, so it is your property. So whatever we are taking the cyclic integral of property, that will become zero. So that's why we have written here. Okay, so cyclic integral of del q upon t is less than equal to zero. So it is known as your inequality of the Clausius. So this relation will also provide the criterion of the reversibility of the cycle. Reversibility of a cycle. Okay. So from this relation, so first we will solve our problem, and then if you are getting the values which are less than equal to zero, so we will find that relation, whether it is the reversible one, cycle is reversible one or irreversible one. So from this relation we can write like this: del q, cyclic integral of del q upon t is equal to zero. In this case साइकिल इज रिवर्सेबल, क्योंकि ds इक्वल टू हो जाती है ना, तो इसीलिए इट इज साइकिल इज रिवर्सेबल. देन del q upon t less than equal to zero, then cycle is irreversible and possible. Okay, so in this case cyclic integral of ds is greater than cyclic integral of del q upon t, है ना. So cyclic integral of ds will become zero. Okay, so this is the reversible process. Irreversible process में always entropy will be greater than del q upon t. So then another relation, that is your del q upon t is greater than 0. In this case, cycle is impossible. Impossible. Okay, because it will violate the second law. Okay, so that's why this is not possible. So it is the Clausius inequality, where we have taken the cyclic integral of del q upon t is equal to less than equal to your 0. So next we will discuss the Tts relation. So it is very much important relation from which we can find out what is the entropy change of the your solid, and what solid and liquid, and also from this relation we can find out what is the entropy change of the ideal gas, है ना. So यहाँ पे दो तरीके के TDS relation हम discuss करेंगे. Okay. So all of you know that we know that from the first law application to the process, there we can write down one relation, that is your Q equal to your uh, mm, del U or delta U. If it is the dq, then we can write like this: du plus dw. Okay, so it is your applicable for the process. So in this case, in place of your dq, we can write that dq is equal to your TDS. So similarly for the reversible process, this will be the dw for the reversible process. क्या था रिवर्सिबल प्रोसेस में वर्क ट्रांसफर कितना है, कौन बताएंगे?
Ma'am, PDB.
TDV.
Integral of PDB.
Okay, so it will be the PDV. So if you will put this relation in this equation, that is the equation 1, so it will give you the TDS equal to DU plus PDV. So it is the first TDS relation. So first TDS relation, this is also known as the Gibbs equation. Okay. So second TDS relation we can find out from our enthalpy relation. Okay. So in this case, first we can write like this: H is equal to your U plus P B. Okay. So H, if you will take the differentiation, it will be become dH is equal to your du, dpv will become p dv plus v dp. Okay. Okay. Then instead of your du, we can put this relation, that is your du will be dH minus pdv minus vdp. Okay, so this du we can put our first TDS relation. It will become TDS du plus pdv. So instead of the du, we can put dH minus pdv minus vdp plus pdv. So these two will get cancelled. Then we are having the second TDS relation, that is your dH minus vdp. So this one is the second TDS relation. Okay. Okay. So here this one we can also write like this: entropy change can be find out from this relation, that is your ds dH upon t minus vdp upon t. ये रिलेशंस में हम यूज करके हम एंट्रोपी चेंज फाइंड आउट कर सकते हैं. Similarly, in this case, we can also write like this: ds is equal to your du upon t plus pdv upon t. Okay, from this relation also we can find out what will be the entropy change. So now we have to find out entropy change of liquid and solids. So which equation we will use to find out the entropy change of the liquid and solid? Okay, so all of you know that liquid and solid, these two are nothing but these are incompressible substance. Okay, so in this case, this specific volume, both specific volume will nearly equal to constant during the compression process. So if it is constant, then your volume will be become zero. Okay, for liquid and solid. So if your volume is zero, then we can use the first relation, that is your T ds equal to du upon t plus your pdv upon t. So this will become zero. Then we will have the ds is equal to du upon t. Got my point? So in this case, we can find out what will be our entropy change. So instead of dtu, we can write that mcv dt, है ना? तो यहाँ पे अगर हम यूनिट मार्च के हिसाब से उसको कंसिडर करेंगे, सो दिस विल बी द cv dt T. So it is depend upon the specific heat at constant volume. It will depend upon the temperature. So it is the function of the temperature. Okay. So this will become CVDT. Then suppose you are finding out the entropy change uh, for any process of the liquid. So let us take that we there is a change of the state 1 to 2. Okay, so in this case, what will be the your entropy change? We will find out. So this is applicable for the incompressible fluid, that is a solid and liquid. So we will take the integration of it, right? So it is the 1 to 2 T. It will give us S2 minus S1 is equal to your CV ln T2 upon T1. ठीक है, ये है आपका एंट्रोपी change for the solid and liquid. So similarly, you can find out for the gas, that is in this case, suppose we are taking the ideal gas, what will be the equation? So in that case, we will take the second relation, then we will find out. Also, you can take the first relation also. Okay. So for ideal gases, we all know that du is equal to your cv dt. Then your P is in that case PV MRT. Okay, that will be the RT. Then P will be become RTB. Okay. So this is ideal gas relation. So in case of that first TDS relation, we will have the DU plus du upon t, that is your p dv upon t. So this will become cv dt upon t plus p dv की जगह में p के जगह में क्या रहेगा, p के जगह में we can write as ft v, this will be the dv upon t. So these two will get cancelled, then it will be r will be common, dv upon v. So suppose we are taking the entropy change of any process which will be taken from state 1 to state 2. So in this process entropy change 1 to 2, it will be become S2 minus S1 integration of 1 to 2. This will be the Cv dt upon t plus r we will take outside, and then it will be the 1 to 2 dv upon v. So this will become your Cv ln T2 upon T1 plus R ln V2 upon V1. ओके, got my point? तो ये है आपका एंट्रोपी चेंज ऑफ आइडियल गैस. सिमिलरली आप सेकेंड रिलेशन अगर यूज करेंगे इसमें, तो सेकेंड रिलेशन मीन्स सेकेंडरी रिलेशन. Okay, if you are using the second TDS relation, in that case we are having dH is equal to your CPDT, right? So in that case, what was the equation? This is the equation: dH upon T minus VdP upon T. dS is your dH upon T minus VdP upon T. Okay, so please find out the entropy change in process 1 to 2. What will be the entropy change? अगर हम process 1 to 2 consider कर रहे हैं, what will be the entropy change by using this equation? Second TDS relation कीजिए और मुझे बताइए. Any one of you, please tell me. Please tell me.
मैम एक बार शो करिएगा.
ये
मैम CP ln T2 by T1 प्लस RT ln P2 by ln P2 by P1 और P1 by P2.
who has given the answer?
Yes ma'am.
Shivam. Your roll number is 104.
No ma'am, 48.
48. available energy and unavailable energy. Okay, so I will explain in short only. But just for the sake of your knowledge, I will tell you. But for the exam point of view, it will not come. Okay, tomorrow I will explain the entropy principle. Okay, thank you all. Sanjit Kumar, what is your roll number? Sanjit Kumar, what is your roll number?
103.
103, okay. Thank you all. Tomorrow you are free at 8 o'clock, right? Say yes or no. If not, then
Yes, ma'am.
okay.
Yes, ma'am.
No issue. Then I'll take 11 to 12. I may extend up to
Yes, ma'am.
12:30. Okay.
Okay, ma'am.
Okay. Thank you all then.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.